Hello students, in this brief PowerPoint presentation, I'm going to discuss several different conditional statements. So let's start by defining a conditional statement. A conditional statement is a statement that can be written in if-then form. If blank, comma, then blank. So let's look at a comical example. If your feet smell and your nose runs, then you're built upside down. So we've written this logical statement in if-then form, so it's considered a conditional statement. Conditional statements have two critical parts, the if part and the then part. The if part is called your hypothesis. It follows whatever the if is. So the hypothesis is the given information, or what we call the condition. The then part, what follows the then, is called your conclusion. The conclusion is the result of the given information. You can take a statement and transform it into if-then form to really emphasize which part is the hypothesis and which is the conclusion. So what we're going to do is we're going to turn the subject into the hypothesis in order to do that. And we're going to look at some examples so that this makes a little more sense. Let's suppose you have the statement vertical angles are congruent. Well, we can transform this into a conditional statement by writing if two angles are vertical, then they are congruent. The congruence follows the fact that they are vertical. Seals swim. That's just a regular statement, but we can transform it into a conditional if-then statement by writing it as such. If an animal is a seal, then it swims. Conditional statements don't just have to be in if-then form. You can also rewrite them using the word implies. So let's look at how this would appear. Suppose that you have the conditional statement, if two angles are vertical, then they are congruent. You can use the word implies and rewrite this in conditional form as two angles are congruent implies, or excuse me, two angles are vertical implies they are congruent. Notice your hypothesis and your conclusion exists in the same spots. Hypothesis in the beginning, conclusion at the end, and implies occurs right in between them. So why do we care about conditional statements? Well, they really lay the foundation for logic in mathematics, and that logic is critical to being able to write sequential proofs, to move from I know this to making a final conclusion of that. Okay, so a conditional statement is false only when the hypothesis is true, but the conclusion is false. A counterexample is an example that is used to show that a statement is not always true and therefore false. So let's look at an example. Let's suppose you have the conditional statement, if you live in Virginia, then you live in Richmond. Okay, so we have a true hypothesis, but let's evaluate the conclusion. Is it true or false? If you live in Virginia, do you have to live in Richmond? Absolutely not. You could live in Weirton, Follansbee, anywhere else. And so you would want to show a counterexample. I live in Virginia, but I live in Glen Allen or Weirton or Follansbee, whatever. Therefore is often depicted with the three dots that are lined in a triangle. So you can use that symbol to say, therefore, this conditional statement is false. Mathematicians are fans of writing less but saying the same thing, and that's why I love math. It's so efficient. And so one way they do this is replacing hypothesis and conclusions with symbols. The hypothesis is often represented with the letter P. the conclusion is represented by Q. So one way that you will see the generic form of a conditional statement is if P, then Q, or P implies Q. Conditional statement is typically written with the letter P, an arrow facing toward the right, and then your Q. That means if P, then Q, or P implies Q. Now you have to define what P and Q are. So one way to do this is write a P, then a colon, define your hypothesis, Q, then a colon, define your conclusion. In the example here, we have that P, the hypothesis, represents a number that is prime, and Q is that number has exactly two divisors. Writing this in conditional form, and this would be a true conditional statement, when you have P implies Q, in English, that would translate to if a number is prime, then it has exactly two divisors. Just as the three dots aligned as a triangle represent therefore, we also use a little squiggly to represent not. And I'm sure you've come across this before. So let's say you want to say not P. Well, suppose that P represents an angle that is obtuse. If you write not P, then that would mean that the angle is not obtuse. So that means the angle could be acute, right, or straight. Example 2. Let's suppose that P is defined as I am not happy. Not P would be I am happy. The not P took the not out. So it would be a double negative, not, which then becomes a positive. Another important symbol is the caret, or the up arrow without the stem. Now you're probably used to seeing this in English class. However, if you've taken any math classes where you studied a little bit of conjunctions and some other probability and logic, then you might be accustomed to this symbol. But it represents the word and. So for instance, let's suppose that we define P as a number that is even and Q a number that is divisible by 3. P and Q would mean that the number is even and it is divisible by 3. So if that were a true statement, what numbers would belong to such a group? Well, for instance, the numbers 6, 12, 18, 24, 30, 36, 42. These conditional statements really force you to think through the logic of the statement as it is written. Just as the upper caret represents the word and, the flipped version of that represents or. And you may recall seeing this with U's and N's when you're working with set notation in the past too. So let's look at a statement that uses or. Suppose that P is defined as a number is even and Q a number is divisible by 3. So P or Q would translate to a number's even or it is divisible by 3. Doesn't have to be both of those at the same time. It could be one or the other. So that would include a much wider set of numbers such as 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, and so on. As a short little reminder, your three little dots arranged as a triangle mean therefore. Since we examine the logic of a conditional statement, we examine the logic of other forms of it. And there are four different forms we're going to talk about. The converse, the inverse, the contrapositive, and then the biconditional statement. Let's start with the converse. With the converse, you switch the hypothesis and the conclusion. So instead of P implies Q, it's Q implies P. So let's start with one of the examples we've been working through without. So if is two angles are vertical and Q is they are congruent, if P then Q would translate in English to if two angles are vertical, then they are congruent. Well, what about Q implies P? That would become if two angles are congruent, then they are vertical. Now, the conditional statement is definitely true. That converse is not true because you can have two congruent angles in some type of quadrilateral and they may be adjacent to one another instead of being vertical angles. So that would be a counterexample showing that the converse would be false. The next form of a conditional statement is the inverse. With the inverse, you state the opposite of both the hypothesis and the conclusion. So we use our little squiggly or not sign. So using again, if two angles are vertical, then they are congruent. If we were to write this statement as its inverse, it would be if two angles are not vertical, then they are not congruent. Now again, you could have two angles that are not vertical, perhaps they're two adjacent 90-degree angles, but they would still be congruent. So in this case, the inverse would be false. Form of the conditional is the contrapositive. With the contrapositive, you switch the hypothesis and conclusion and state their opposites. So it becomes not Q implies not P. So again, if our conditional is that if two angles are vertical, then they are congruent, not Q implies not P would be if two angles are not congruent, then they are not vertical. Think about that for a second, and we're going to talk about a relationship that exists between the conditional statement and the contrapositive. So in the previous slide, we examined the contrapositive of our conditional statement. Remember, the conditional was, if two angles are vertical, then they are congruent. Our contrapositive was, if two angles are not congruent, then they are not vertical. Now, we know our conditional is true. Is that contrapositive true? If two angles are not congruent, then they are not vertical. Is that true? Well, yes, it is. If you don't have two congruent angles, if they're not equal, then that they fail the definition of vertical angles. Here's the thing. Contrapositives are logically equivalent to the original conditional statement. In simple English, if the conditional is true, the contrapositive is true. If the conditional is false, the contrapositive is false. They mean the same exact thing. So why don't you take some time and fill out this table? It just gives you some practice with writing the conditional, converse, inverse, and contrapositive in symbolic form in English, and then evaluating its true or falseness. Now you're going to do that for the example of P, your hypothesis being the triangle or a triangle is equilateral, and the conclusion being the triangle is isosceles. So take some time, fill out this chart, pause the presentation, and then you can proceed to the next slide, which has the solutions. So we know the conditional statement is true. If a triangle is equilateral, then it's also isosceles for sure, because an equilateral triangle has greater specifications than the isosceles, but meets all of those that would define an isosceles triangle, insofar as having at least two congruent angles with two congruent sides. But then we have to consider the logic um, that would be implied by the converse, inverse, and contrapositive. I'm going to skip down the contrapositive because if we know that the conditional is true, the contrapositive also must be true. So let's evaluate it. Remember, it's not Q implies not P, so that would mean that if a triangle is not isosceles, then the triangle is not equilateral. That is 100% true. If it's not isosceles, that means it does not have at least two congruent angles with two congruent opposite sides, so therefore it would fail by definition of equilateral triangle as well. Let's hop back up to the converse. The converse, we just flip the Q and the P, and you get Q implies P. If a triangle is isosceles and the triangle is equilateral, well, that would be false because you could have an isosceles triangle. It could be a right isosceles triangle, for instance, where you have a 90 and two 45s, and that definitely is not equilateral. How about the inverse? Not P implies not Q. If a triangle is not equilateral, then the triangle is not isosceles. Well, that is for sure false because you could have a not equilateral triangle, which could be an isosceles triangle, and so therefore it is isosceles. A special type of conditional statement called the biconditional statement. The definition of a biconditional statement: it's when a conditional statement and its converse are both true. And so therefore the two statements can be combined and you use the word if and only if, which can be replaced with the symbol or the letters IFF. So let's suppose you have the conditional statement, if an angle is right, then it has a measure of 90 degrees. So your hypothesis is the angle is right, conclusion measures 90 degrees. When you examine the converse, if an angle measures 90 degrees, then it is a right angle. It holds true, as does the original conditional statement. When that happens, you can write it as a biconditional, and you would do so as follows. An angle is right if and only if it measures 90 degrees. Many definitions can be written as biconditionals. Not all of them, but many.